Hello everyone, today we're back again on AtCoder Beginner Contest 308. It starts in about 20 seconds. I don't know, I will probably do it like, maybe this will be better. As usual, just having the both. Yeah, check out my my channel for other screencasts and other problems in programming. So, okay, let's start. Given integers, print yes if they all satisfy the following three conditions. The sequence of these 8 integers is monotonically non-decreasing. These are all between that and they're all multiples of this. So, okay, let me just call that. Maybe I need to zoom in just for the... So there will be 8 integers. What I will do is I will have like a vector... wait, I will just do this. Bool OK one. OK is like if it's sorted, so is sorted A begin A end. Then we go up to 8 integers. For each we check also that the integer AI is bigger than 100, smaller than this, whatever that means, and A of I is divides this. That should work. Okay, B. Takashi ate n plates of sushi at sushi restaurant. The color of the ith plate is represented by string CI. So by some string here, the price of the sushi corresponds with the color of the plate. For this, the sushi color, whose color is represented by a string di, is worth pi in a plate. Okay, find the total amount of all right, so for each of these colors we're going to map some price to them. So let me just see that here, N and M. N is about, so M, there are M different colors of sushis. D is, well, what? The blue plate P1 is worth the price of sushi corresponds to the color of the plate. For each I, the sushi whose color is represented by a string di is worth pi. Okay, so this is the string and this is these colors. Why are there 2 instead of... Is it a wrong? No, here's the same idea. There are 3 of these PIs. Yen is a currency. If the color does not coincide with any of this, it is worth P0 yen a plate. All right. Oh, so there's some catch here. Okay. Let's read N and M. Then we're going to string what he ate here. He ate N of these, right? Yeah. 8, not eat, but whatever. So then there are some strings here. So colors. Then there is this here. So I want a map of string to integer, and then I want so this is some kind of map, and then map of colors at I. So just if I is a positive number, else just remember P0, and P0 is here. So if it's a positive number, map of colors of I minus 1 is equal to X. So we map all of the colors, we have P0, then we go what he ate, and then we find in the map if such thing exists. If it doesn't exist, we add P0, else we add its cost, and then we do this. To find the cost is just second in that pair. That passes. We're just going to submit. We got AC on A, so that's okay. And so C, n number of n people, number from 1 to n, toss the coin several times. We know that the person I tosses resulted in AI heads and BI tails. Person I success rate is defined by some formula. Sort the people in descending order by success with ties broken in descending order of their assigned numbers. So this is just teaches you about sorting. So teaches you about sorting these. I will show you how I do that. So there are n people. Then there is like some vector of A and some vector of B's. And then I can just input like these. Or maybe this is better just for this. Then what I do is like I do some order. I fill the order with consecutive integers starting at 0. This is how you fill the order. Then you can sort the order here. Then you can sort the order by some custom comparator, and this custom comparator can access these A and B's. But what you see here is, because this is like division here, it's essentially what he is doing is essentially saying like this: A of I divided by, so A of A divided by A of A time plus B of A should be bigger than A of B divided by A of B plus B of B, right? So this is for the A side, and this is for the B side. So this is for the X and Y or whatever sides. X and Y have been better to choose, but whatever. Now I will just move this here, and instead of dividing it by here, I will multiply it here. And this I will do this. So I will copy. I will multiply this on this side, and I will divide this on this side. Now, because multiplication can overflow, I will make them long, so I don't have to cast them all the time. I just don't lose. It's fine. So what is saying is this. Okay, first we are going to check if they're both equal. If they're both equal, then I will return that A is smaller than B. Else I will return that this is the case, that this here is bigger than this here. And then I will just print out the order. Oh, not that. Oh, are they equal? Maybe. A times this should be in brackets. Yeah, of course. This should be in brackets here. All these. Just add them in brackets here. Just yes, and this should, of course, this should be in brackets as well. Just don't forget brackets. I will just plug that in. Okay, let's go D. So D here seems like some interesting problem. We'll see. We have a grid H horizontal rows and W vertical columns. The letter written in this equals to the string. Okay, just pretty straightforward. Snook will repeat moving to an adjacent cell, sharing a site to travel from 1, to height and width. So he will travel like that. Determine if there is a path in which the letters written on the visiting cells are snook in the order visiting adjacent cells. Formally determine if they're... So, yes, so this is a pretty straightforward dynamic programming problem. And this problem is just straightforward, in my opinion. So what you do is you do a three-dimensional dynamic programming. So first let's read this matrix. I will call it A. I will read this matrix. Then I will create a so there's enough memory. So, I mean, of course there is. I will create a DP which but why it's like 500 times 500? There's no need for that, but whatever. Okay, so this is 5. So this says like have I been here at this letter, and then what I will do is I will do this. So if A of 0, 0 is S, then dp of 0, 0, 0 is 1. And then if so I'll say okay is, so I'll say like this, dp is 1. Else if it doesn't start with S, I'll just say no, it's impossible to do that, and I'll back off. It doesn't start with S. But after that, what you will do is you can always travel in adjacency, right? In adjacent cell. But you can travel as well in the reverse order, right? Oh, now it's not that simple. JSON determine if the I mean, technically, yeah, technically, so you could use a BFS here. Like, in order here, the JSON cells sharing a site if and only if that's the case. So what you do is like you push a BFS, and this should work. A BFS should work. So I will just say where I am and in what letter I am in the alphabet. So that's yeah. So let's create a structure. This structure will contain X, Y, and letter. Here I will push to the BFS structure of 0, 0 and letter 0. While BFS is not empty, I will get this letter here. Get this letter BFS dot front with some Q. Then I will move through all 4 directions. That's probably the easiest thing to do. I always code it like this. This is my preferred way of coding anything with BFS. Here I just need valid to say if it's valid. So I have this valid snippet that I just do. I just need to supply N and M as well. If it is valid and at the new X and new Y there is a character, so minus actually it doesn't, yeah, minus A. If the character, if letter plus 1, letter plus 1 modulo 5 snook at this letter plus 1 is equal to, so I add 1 and then modulo 5, and then now this snook is just a string snook which has the letter snook in it. So if snook at the next letter is equal whatever I am next at, and one more thing here, let's just make it in a new here so you can see better. And one more thing, dp at new X new Y at L plus 1 module 5 is not visited, so this is not visited. Then what we're gonna do is we're going to say dp new X new Y L plus 1 module 5 is visited, and then BFS push new X new Y L plus 1 module 5. So this is the new ladder. And then at the end I just want to see if it is possible for any bool, so I'll just iterate through all of the 5 ending letters and see if dp of n-1 m-1 I is possible, then just say yes and return. Otherwise we say no. And this okay, so no, okay, so that should letter 0 0. If that and the next letter oh, not -1, but -a, no, here it's supposed to be like this. It's supposed to be like this. So I don't think there will be TLE. There shouldn't be TLE, because if it's like a cycle, it would just like, it would not visit again. So yeah, gets accepted. So okay, now we go into the more difficult portion of the problems. You're given a length of n sequence consisting of 0, 1, and 2, and a length n string consisting of m, e, and x. Find the sum of this over all tuplets of integers, and si and j is equal to max. Interesting. Interesting. So this here kind of suggests, so first of all, the answer for any of these maxes would be either 0, 1, 2, or 3. For any of these tuplets of integers. So let's take a look at this. For each e here at the center, for each e, can we somehow know how many m's and the different frequencies of m's on the left side and the different frequencies of x's on the right side? So for all of these, then we can match them and somehow calculate for this specific e. So for each e, we're just going to calculate this, and we're gonna have like 2 data structures, one on the left side and one on the right side. Because there's no symmetry, it should be a fairly easy problem to compute. Okay, so let's see how we're gonna do that. Fairly, I'll say straightforward till now. So all right, then yeah, so there will be some answer. On the left side, we want to keep how many 0, 1, 2s we have, such that there are on m. So there's like a frequency array here, left, and frequency right. Both of these should only go to 3. Let's go to 4, doesn't matter. So yeah, so we're going to fill the right array first, and this is pretty straightforward. How you fill the right array is you go through each of these numbers, and then you say if s at I is equal to x, so on the right side we want just x's, frequency right at a of I plus plus. This is pretty straightforward. Okay. Now left is empty. Left is empty. But now there is this calculation. So we are going to remove from the frequency right if s of I is equal to x. We're going to remove, we're going to say frequency right a of I minus minus. So what we want to do essentially is wait, do I need to remove the first element or to even include it? So kinda no, right? I mean, we could just do this. We could do this. We could actually start from 1. Here, include all of them. Then here, we could start from 1. Actually, I mean, no, we're gonna do this. Doesn't matter if one edge case is fine. So we remove from this element, and then we say, okay, we have to add the previous element to the left side. So add this element to the left side, and this is if s of I is equal to m, frequency left is plus plus. Okay, and now here is like how you calculate it. So if I first it has to be positive because there won't be element on the first index. Okay, so now if I and s of I is equal to e, so it has to be e, then there are some elements m to the left side, and then there's something from the frequency on the right side. And now we need to just compute all of these possibilities. So we're just going to compute for each on the left side, just going to brute force that. For each on the right side, now I know what is my element, it's AI, so I will just say, okay, so I'll say this, my element, so I will just create a vector of Boolean visited. So this is like max of so this is max of L, R, and A of I. So the max of A is some integer, so let's say result. This is some result, right? Now the result will be multiplied by how many frequencies, so the frequency of from the left of L times the frequency from the right of R. So that's thing, and this will be added to the answer. Now this should not maybe overflow because this is okay. Now inline int max, and then there are 3 integers a, b, and c. So these 3 integers will vector boolean v of a is 1, v of b is 1, v of c is 1, and then if it's not visited, return I. So if it's not visited, just returns I. Why is here returns I? So that should kind of work, right? Of course, print out the answer. Okay, that passes. Just submit it. I don't see any overflows or things like that. Should be fine. Maybe just wait for the judge if there are some edge cases that we didn't account for. But there shouldn't be. So okay, it gets accepted. Okay, F. Now we're doing good. You're in store to buy n items. The regular price of the ith item is pi. You have m coupons. You can use the ith coupon to buy an item whose regular price is at least li at a DIN discount. So you have some threshold in which that coupon actually goes. Here, each coupon can be used only once. Besides, multiple coupons cannot be used for the same item. If no coupon is used for an item, you will buy it at a regular price. Find the minimum possible total amount of money required to buy all n items. So there, for each coupon, there are some prices here, and then for each coupon there's L and D. Okay, so I'm already thinking about some greedy things here. So greedy solutions in if you kind of take a look at the interesting, very, very interesting. For the largest threshold coupon that has the largest threshold, also linearly does not mean that it has. There could be a coupon such that it's like smaller, but it gives more, and then there's like a larger coupon threshold, which there is this principle, like you can exchange that without losing the optimality of the problem, and this means that it is kind of so it is greedy. So regular price at least y. So what about like sorting the prices in descending order, and then as soon as we have some coupon that we can use, the largest coupon, we use that on that price. If there are multiple coupons, we use the one that gets the most discount in that price range. But not necessarily, because you want to also be able to use that one. So not necessarily. So if we draw that graphically, I always draw it graphically because you could kind of, that's a bit sensitive for me, but you kind of imagine that you have, oh, what is this sense? Is it so? I don't know why is this sensitive, but like you can imagine there are some prices like this graphically, and if there is a coupon that is like at least this here but has like smaller price, and there's like a coupon that is like at least to here, like at least this price, but the discount is way bigger. You don't want to use this coupon here because you can use this coupon somewhere later in the process, but this coupon has to be used here. But if you cannot, if there would be only this kind of gentleman here, if only the prices consisted of one very large thing, let's say, then if I have one coupon that like it's like this here, very small, and then one coupon that is like this here, larger, you're gonna use the larger coupon, because let's say each of all the other prices just are just too small to use any of these coupons, right? So in some sense you want to kind of use a coupon that is largest in the gap between the price from here and the price to here. So in this gap, you want to kind of use what is the largest coupon that I can use in this gap. So I am kind of thinking about sparse segment trees or some things like that. Maybe there is like without segment trees, just like a priority queue solution or something. So, but is that optimal? I mean, if you don't use this coupon, definitely there will be. But sometimes, do you kind of want to use, yeah. I mean, there could also be, wait. So what if I have multiple prices that are used in, so whatever, I will take the large, so let's say that there's multiple, so I'll definitely take just the largest coupon that like I can, no, I kind of, wait. Yeah, so let's say, let's say there are two prices, and one of them like you have this coupon, let's say that demolishes like to here, this coupon, and let's say one more coupon here. Then you kind of then there are more coupons than their actual like prices. So even though there's nothing here in this gap that I can use only here, there are, even though if like there could have been a coupon here, but could have like been like this, so the mulch is very, very little. Like this coupon just has like a lot of yen, but this here doesn't. So you kind of wanna use like, let's say this, and then you wanna use maybe this and then this, and these would just like never used. So if you think about this, each coupon can be used on some segment of the prices. So if there are some these prices and you see like a coupon that is like here for this L, let's say that this is the lowest thing, then this means that this coupon can be used in these prices. It's like a range, because we have sorted. And let's say there's coupon here, can be used in these prices, there's coupon here, doesn't really matter, but all of these coupons are just being used like that in some prices. Then what we want is so the problem boils down to some intervals that we need to choose some suffixes, not intervals, because it would be harder problem probably, but some suffixes, and for each of these columns you need to match, you need to make the largest, so you want to maximize the largest intervals taken by each of these here. So you want to match somehow each of these with some interval below. Okay. So in essence, this is the problem. We don't care about the height of PIs. So PIs just don't matter at all. It just matters like when we get these intervals in the suffixes, which are in fact like where PIs where PI influences this, like where this interval starts, of course. But when we get these intervals, we can just like don't care about PIs. We only care about in each interval we're going to try to take the maximum intervals for each of like the points here to maximize the sum. So let's say let's say this will take this interval, this will take this interval, this will take this interval, and like that's like the optimal solution. So when we have the intervals, is how can we code it greedily? We can say that there are some intervals starting at this point. So the end point of each interval is the same. Can be taken anywhere whatsoever, anywhere. But for this guy here, well, to take an interval, as soon as he gets like an interval, he wants to take the biggest interval possible. Is that correct? Why? Yeah, so that's correct. That is correct. Because if it doesn't take the biggest interval possible, then it could just be in waste. If in fact it takes the biggest interval possible, doesn't like, it's excellent. It's, I mean, should be fine. I will start coding this. So how do you know what is the biggest interval possible? So like there are some events that I will add, so some starting of the intervals, and then there will be some stack or priority queues that go and then like takes the interval, the biggest interval possible, or something like that. In fact, so I will first have these prices. I will sum them up. I will sort them. I will go through each interval, so each of these intervals will be, so let's first we're going to know D and L, so L and D. I just want to have a clean code, that's why I'm okay. And then what we're going to do is we are going to make them into so there will be wait, how do I, yeah, so I will do this. I'll do this. I will have a these are going to be called events, and I will go through each of these. I will search where the lower bound of this, so lower bound of P and of L of I, so this is the lowest point. In this lower bound, events at this lower bound, I will push back T of I. Then I will make like a priority queue. So the priority queue is just of an integer, right? And then I will go through all of these and here. If there are for each event in events of I will push them to the priority queue. I will take the sum here is going to be taking priority queue dot top and priority queue dot pop, and then I'll just print out the sum. Oh, if PQ is empty, then I'm just going to continue, of course. Okay, this passes. I will just submit it. See if we get wrong answers. Apparently it gets accepted, so it's a greedy strategy. Okay, minimum XOR pair query and make Q. Okay, so how much time we have? We have 50 minutes left on G. Yes. And I registered unrated, so that's a lucky. I thought that I won't be able to maybe finish the whole contest, so I registered unrated just so I don't like lose rating points if I can't make it full. But whatever. There is a blackboard on which you can write integers. Initially, no integers written on the blackboard. Given Q queries, process them in order. The query is of one of the following three kinds. Write an X on the board, erase an X from the blackboard. At this point, this query is given. It is guaranteed that at least one X is written on the board. Print the minimum possible bitwise XOR of two of the integers written on the blackboard. At the point this query is processed, it is guaranteed that at least two integers are written. Interesting problem. So if there are duplicate X's, it immediately means it is 0. The XOR is 0. So if there's like 10 here, we add 10, and we add here 10 again, that immediately means that it's 0. But if not, it means that there exists an XOR such that, like, so it means some you need to find this. Like, how do I find this? So let's think about this. We have some numbers. That are written on the blackboard, and we want to find a pair such that the XOR is minimum. Want to find the minimum of like all ij pairs such that A of I XOR A of j. This we want to find the minimum. These all go up to 30, so they're huge numbers. Let me just see the standings. No, that's not bad. Minimum XOR pair. So how do you find the minimum XOR pair? The highest the bit, so if it's probably like some bit things here. Like, what if a trie? What if we built like a trie or something? Right, this query, print the minimum possible bitwise XOR of two integers, is just like, it doesn't change anything. So this query is just like, okay, we know what this has been, and we can just print it. But then the erase operation comes if the X operation. So if we built like a bitwise XOR like trie, right? if we write an integer, it's just very easy. When we go through the trie, we see what integer is like has like the minimum XOR with like this integer, right? And then we add this integer to the trie. Okay, so that's how we add this integer to the trie. Okay, now we update some answer somewhere. And we can always like update this answer, minimum of all of these. But now erasing, it becomes complicated because this answer kinda depended on some answer that this was originated. So what we are erasing here, actually, like when we erase some number, this number, when we have added this number to the blackboard, it means that, okay, maybe this number updated the answer with some other number here. This is possible. Also, what is possible is maybe some other number they took this as like the minimum. And I don't think actually, I don't know if is it a trie, the binary trie. Can we? Oh, actually, like a suffix trie. Yeah. So like, okay. Huh. Yeah. Like, okay. So let's say it like this. Did I move something? So let's say it like this. So we have some trie, and then we add some. And then we go and then we add another. So here is like we have some count, and then we add some like another. But here we switch. Instead of 0, here we make 1. Here so like 2. Here let's say 0, here's 0, let's say like that. And then again you add like 0, 0, 0, and then you add like 0, you add here 0, 0, 0, 0, and then you add another 0. So now these all counts up. So they count up. Okay, and now I'm just curious at how many zeros can we like, okay, we kind of start here, and then we go as much as we can until we have like twos. And it's in the 0 direction. But here, let's say they split, right? So here they split. Here is just 1 and here is a 0. So do you go DFS and construct both of these numbers somehow? That could be it. When you get to a splitting point, or you get to a point where there's like only one, so you would always get to a splitting point on like 2, and then the thing is that the splitting point you will never, oh yeah, you would somehow, what if there was like 1 here and then there's like 0 here, but there's, you kind of don't want to split here, right? Yeah, of course you don't want to split here. But if there was like 1 here and like there was 0 here and here's only like 1 count, then you just can't go here. If you go here and here, you kinda XOR these both. If you go only here, then you XOR that 1 with the thing. So I would guess it's a binary trie, just a binary trie, where you keep for each node, you keep the count as well. Then okay, let's get all of the edge cases down before we start writing this. Before we start writing, we have to get all the edge cases down. So if there's only 1 path, we take, of course. If there are 2 paths, and so it means 0 and 1, and there are not there, if there's like 2 here, then we take this. If there are 2 paths, but here it somehow it splits into 2, we have to split it. We have to split our DFS. And then from there on, we just kind of maneuver this DFS through the tree somehow. There won't be another case here because it has to be split here, so it has to be 2 paths. Yeah, so okay, let's try to code this. What about EX? Just maybe to read it simple. There's simple under graph initially required to, and the cost required to paint it black is CI, so there's an edge. And making a queue means painting 4 or more edges, so that there's a cycle painted. The edge painted black, not forming the cycle, connects vertices on the cycle and other not. This is some heavy graph theory problem, I would say. The edge painted black, not forming the cycle, connects a vertex on the cycle and not vertex on the cycle. You kind of maybe, yeah, this is some very hard theory. But n goes only to 300, which means maybe something. I don't know. This is very, very weird. because ci goes 10 to the 5, that means it could maybe in linear time ci's or something. But it's weird. So let's try this. Let's try this. Okay, so there's some Q queries. There's some trie, so trie. This trie will be okay, type of a query. If t is 1, then there's some integer x, and then you need to call the trie to insert this integer. Then delete this integer and print something in the minimum. Okay. Each trie will have a vector of children, so children, 2 children, which both are null pointers. Then we also want like the count. And now the functions. One function will be to insert a number. So to insert some number x, we need at what bit it is, this number. First we started like bit 31 or something like or 30, just probably is enough. This is probably enough. This is where we start the number. Then yeah, so the digit is x and 1 LL bit, right? So if bit is set to if bit set to -1, then we want to return. This is not it. This doesn't need to be out. So this is the digit. Now if C a digit is null pointer, then we want to create a trie there. C a digit is new trie, just new trie like that, and then C a digit insert x bit minus 1. Also, we need to somehow get the count in, so somehow the count has to be updated. Okay, now we kind of want to erase some integer. Okay, and it's the same idea. If bit is -1, return count minus the digit. So it's the same idea, but here's the thing. So like, okay, so the digit is this. If there's no way it will be null, because there will be already a digit there, and then you just call arrays on that. So count minus minus. Okay, so we kind of now can try insert a digit and try erase a digit. But now another thing we need to do is this DFS, and this DFS is like, okay, DFS, and so this DFS is not going to the tree, but it's like just traversing it. Bit. Okay, so this is, there's no X, so there's, you start at the top and you have like two kind of, I don't know if I want to traverse it inside the trie. Maybe outside the trie will be better. Yeah, maybe here will be better. So let's see if this crashes anywhere. So let's just we insert 10. Why? What's the idea when we insert 10? If it's a null pointer, we create a trie. We create a node. Then we insert that. Oh, it doesn't even print 0. Okay, so on the first insert something fails. Impet in X. Of course, this is just a boolean. So this is just a boolean expression. Yeah, so that works. Now that that works, we want to kind of traverse the trie by doing like two pointer things you can do. So you have like pointer 1 is the trie, and pointer 2 is the trie. Why? What's that? Then while P1 is not null pointer, while P1 is not null pointer, then we will traverse it. So if P1 at 0, P1 dot child is 0, if p1 now if p1 is not null pointer, I'm thinking about like these edge cases. It comes to the end, and then if p1 child is not null pointer and p1 sees, so I'll say like this first: p1 is null pointer and p1 child 1 is null pointer. Then I'm just gonna break. Okay. I think that's enough. So if both of them are null pointer, that means I'm at the end. I don't move any further. But so if both of them are null pointer, okay. So what if child 0 and child? So how do you simply but what if, wait, what if both of them are 2, 2? What if we have something like this? So like you have like 4 here and then you have 2. You could take both of these, right? You could take this and go somewhere here. And you can take this and go somewhere here. That does not sound good. Kind of want to merge them together, maybe. Okay, so my camera just doesn't want to connect for some reason, and the contest ended, so the last 15 minutes I didn't do anything. But so I will now go through the usual explanations of all of the problems. Sometimes some things I will skip, but at the end I will just take a look at the tutorial for G, for problem G, that we did not solve during the contest. So we did succeed solving everything through F, so that's a good start. Let's go through the tasks one by one. So yeah, so the first task was task A, which just required you had some integers and you had to see if all of these check out. The thing you had to see is just, I mean, this is sorted. It helps you to see in linear time if something is sorted. I just use that and plus some ifs here, something. So okay, and this sign, I mean and, means that like this has to be always true in order okay to be true. So if one thing, this, if it's 0 somewhere, it's just okay, it will be always 0. yeah, that's pretty much A is pretty simple. B also is just so you need necessarily to use a map at B, but using a map just simply it makes the coding much more simple. You had some dishes that you ate. These were the dishes that Takahashi ate, right? Then these corresponded, like red corresponds to this, blue corresponds to this, red corresponds to this. This is the price of this dish, and any other dish which is not of blue and red or whatever thing it is, it corresponds to this P0. This is the default price of dish. And you just first you input P0 here, and then you go through this and you map the color to some price. Then you go through each of the dishes you ate. You see if that dish has some designated price. If it doesn't, just add P0. Else add the price of that dish. Pretty straightforward. Nothing here to write home about. See standings. Here standings, you usually when you see something like this with a fraction, many times you could make this, instead of a fraction, you could make this multiplication. Why you want to do this in this problem is because you would encounter precision errors if you do it as a fraction. So it's just with a simple mathematics here. So I have like some vector order, which I will sort this order by some comparator, and this comparator is just like fixed. I mean, you could do anything in this comparator, really. But what I'm saying here essentially is, okay, so you have this fraction has to be bigger than this fraction. What is defined? So the people in descending order. So this has to be bigger than this. So the first A denotes like the element before B. So it's in this order. So A has to have a bigger fraction than B. So or this could be X and this could be Y, and then I need to exchange all these there. But okay, whatever, doesn't matter. So this has to be bigger than this, right? But you could imagine it another way, is like if I multiply this fraction by this here, it will cancel out this, but on this side, so I could essentially move this on the other side and move this on the other side and get another formula which is equivalent to this formula. And this inequality is equivalent. So you could just first check if they're equal, then like return if A is smaller than B. So this says that if the index A is smaller than the index B. Otherwise, because it says with ties broken in ascending order of their assigned number. So ascending order. So it means if they're equal, just ascend order. And you say that otherwise you just use this inequality that we come up with, and then just like print the order. +1 because of course it's one index. It's one index. So that's pretty much for C. D, let's see, D. Yeah, D was okay problem. So you had this thing here, and then you needed to do like you needed to just walk around, but always walk around in this pattern snook. It would have been cooler if there's like Snoop instead of Snook, just for like Snoop talking, but whatever. Okay, so I will have written Snoop here just for the memes. Okay. In the order of visiting, so you could just go adjacent cells, and this is essentially what I did here. Is like I had this DP, or like this visited thing, but each cell had also this vector where you say in what letter did you visit this cell in. essentially saying that I don't even need that. Now that I think of, because the letters don't repeat. I don't even need that. The letters don't repeat, but it doesn't matter. I just push BFS and that's it. Just push BFS. And then track in which letter am I currently on, and then if it's the next letter in the word, then I can go there. But if it's already visited, then I don't need to go there because I have already went there, so it doesn't matter. BFS does the job. DFS will also do the job, but I mean, recursion limits, you have to be careful. MEX, problem E. So problem E is a typical data structure DP problem. So this problem kind of asks you this to find this MAX over some tuples, which have the condition that the string is first this tuple is M, then E, then X. And when you have three something, you could always take a look at it in a way that you would fix the middle element, and then with some data structure in the front and some data structure at the back side, you could do some manipulation with matching these two data structures if the middle element is fixed. And what I'm doing is essentially this. I have two data structures in a sense way, two arrays, frequency of the left, frequency of the right. So frequency left means how many times 0, 1, 2, 3 on the left side have come up such that they are on an M ladder. So they are adjacent to the M ladder. So I mean they are on top of the M ladder. They correspond with some M ladder. On the right side is X. On the X ladder, because if on the right side I have an M ladder, I don't care about that M ladder, because this E that I'm currently at, so I will be always currently at some E. So this E, it only corresponds with some M's on the left side and some X's on the right side. And then you need to brute force, essentially what I do is just brute force. I brute force, okay, for each of the occurrences of L on the left side that correspond to some M. So if L is 0, it means that there is 0, and then on bottom there's an M on the left side. And then on the right side, on the other side, I just look at X's where they are. So with for all L, for all R, and for AI, so I don't know what AI is, even though E is here, it could be 0, it could be 1, it could be 2. I find this max, which is just a function, which I wrote just here to I don't care, it's just some simple function to find this max here of 3 values. Then the answer is actually the result is contributed. How many times this result is contributed to the answer? It is contributed exactly left time, the occurrences of how many M's on the left side there are with that specific L, and how many X's are on the right side with that specific R. So these are the combinations that I could pick and match with that E that I'm currently on. This is pretty much it. The problem, very, very cool problem. Like these problems. F is a really cool problem in a sense of way that you had to see about this. I mean, I don't know if you had to see about this, but I saw it in a way of an interval things. So if you, I explained how I saw that. If I have some L here, if I sort all of the P, so all of the prices, and I have some L here that says, okay, prices above this point can use this coupon, then it says that on this range here, each price, each of these like items can use this coupon. So starting from here to here. And what actually I'm doing is I'm essentially having a priority queue, a global priority queue, some priority queue here. I don't care. And exactly like if there is a coupon, if there is a discount here, so like there's discount here that actually like is valid for all of these prices. So this discount here is valid for all of these prices. I will add it to the queue, and I will always add to priority queue these discounts. But for each price, I will always also pick a discount that is the maximum possible discount in this priority queue. So if it's not empty, I will pick the maximum possible, and the maximum possible discount is always top. So in the priority queue, and then I will pop that. So essentially for each, so I find the ID of where that element, where that discount can be started, it starts to be actually like available to use for all of these next prices. I add it in that event, right? And then I have like priority queue, and then go through all of them. I add all of the prices that now can be used, all the discounts now that can be used. And then what I do is just like, okay, if PQ is not empty, then grab the biggest discount I can use and use it. It will always be valid to be used. The biggest discount never will go into negative, because the here it says this constraint. DI is always smaller or equal than LI. The discount will always be smaller or equal than the lowest possible point that the discount can be used. This is F. G. So G kinda like first for me it looked like some binary trie that you need to do binary trie, and then but I found this way of this, what I was telling about, if there are two paths which are valid, then you have to check both of them. And when in a trie you have to do it, it means that the optimality just breaks down. You have always to go through one path, or to two, or to constant number of paths. You cannot go to like a linear or some like number of paths, because it would just break down the complexity of the trie. You could do it with some kind of trie, but you need to like somehow to merge these when like you add it, and then you see like this is then you need to merge, and then you need to go here maybe, and then you need to merge. So like there will be some merging and unmerging of the tries paths. And when this happens, it just like makes the problem a gazillion times more complicated. But the tutorial says that this is true, and the minimum of x XOR y and y XOR z is always smaller than the minimum than x XOR z. So it means if there is a number between x and z, so like here for x, y, and z such that y is in between z. So if there is a number between x and z, it will give a smaller XOR with some of these two, with either x or either z. And they prove it. I haven't actually read the proof, but the proof seems small. So in binary representation of x and z, suppose that the k plus 1 is so, unless I mean, yeah, I like it. I thought it was something like that. It was I thought something like k plus 1 less significant digits. So like these less significant digits are the same. These some digits are the same. In case least ones differ. then the XOR is bigger than 2k, so yes, this is correct. Regarding this here, if k is significant, if k is significant bit of y is 0, then so I kind of understand it. Yeah, kind of understand it. So he picks some bit that is not the same in x and z. So there will be some bit that is not the same in x and z. And what he does is he says, okay, let this bit be kth bit. Then there is some y, but y is now like y will be in the middle of these two. So it's either this y bit will have all of these the same bits after k, the same, but this also k will be like either up to the x side, either 1 or either 0, and one of them will coincide either with x or either with z. So in fact, you must, the XOR between these two must be smaller than 2 to the k. I mean, yeah, okay. Well, and then like he says like one can track the XOR of adjacent values by addition and deletion of them in a set. And then the answer is just like specifically when adding a value, add the XORs of the previous and next values to the candidates. Removing a value also should update the set as well. And then the set contains this minimum as the beginning element. Pretty straightforward problem when you read, when you know this property. This is maybe a property that everyone should know. Yeah. About E, I didn't even think about this problem. This is cycles, so you have to either somehow enumerate or something about cycles, but I don't know. I haven't even thought about this problem. So yeah, thank you guys so much for watching, and I hope to see you next week on AtCoder again.